We're continuing on with studying submodular functions. And in particular, we're interested now in understanding how we can maximize or minimize them, perhaps in a more general setting. So thus far, we've only talked about maximizing submodular functions, subject to a Matroid constraint. And we saw in previous lectures that if the function is monotone, then the greedy algorithm, natural greedy algorithm, gets us a 1 minus 1 over e approximation. So let me just write that again. So from the previous lectures, we saw that the greedy algorithm guarantees a 1 minus 1 over e approximation to the problem of maximizing f of s subject to s less than or equal to k. This is another way of saying that s has to belong to the independent sets of the uniform Matroid. So this is a uniform Matroid constraint. When f satisfies two properties, it's submodular, and in addition to that, it's monotone. And you can remind yourself, look back to that lecture where we give the proof and see exactly where submodularity is used, where monotonicity is used. And it turns out that actually this is optimal. So greedy is actually the best that we can do. And this is a theorem that's due to Feige. And it says the following: for any epsilon greater than 0, it is hard to achieve anything better than a 1 minus 1 over epsilon approximation. To achieve a 1 minus 1 over e plus epsilon approximation for a specific problem that is monotone and submodular. And that specific problem is the max k cover problem, which I'll tell you about in a minute. For the max k cover problem. So this is the theorem. Let me tell you what the max k cover problem is. This says the following: given a ground set E, some finite ground set as usual E, and now given subsets of E, S1, S2, S3, no assumptions about whether or not these are nested. I'm sorry, whether these have intersection or not. I'm given M subsets of E, and of course the value k, which is, the problem is trivial unless it's in fact strictly less than e. What we want to solve is the maximization problem, which says select k sets that have the largest cardinality of their union. So in other words, maximize the union over all little I in set I, Si, subject to I less than or equal to k. Okay, so it turns out that 1 minus 1 over e is it's NP hard to approximate this particular problem better, and I'll leave it as an exercise for you to verify that greedy indeed gets 1 minus 1 over e approximation. Again, that should be I think you know what to do given what we've seen in past lectures. And you can see that this is just a uniform Matroid constraint there. So this is where we are so far. So we have limited results, but good results for maximizing a submodular function subject to the uniform Matroid. So there's lots of things we could ask about. We could ask, and this theorem says that we can't improve on greedy. So we can't think about another polynomial time algorithm that is going to guarantee a better than 1 minus 1 over epsilon e approximation. But we could ask about maximizing submodular functions, possibly with removing some of the assumptions. So for example, and what we're going to turn to next is generalizing the Matroid constraint. So rather than having it be a uniform Matroid, we can ask, what if we want I to belong to a general Matroid? Then how well does greedy do? And is that the best possible? And also we can ask about potentially removing some constraints on F. Could we remove the monotonicity constraint? Well, you can check, though we won't talk about it in this lecture, that greedy does very poorly if we don't have monotonicity. So even though in the proof it's only used in that one in what appears to be an innocuous way, it's actually very important for the guarantees of the greedy algorithm. So that's maximizing, and of course we can also talk about minimizing and ask, can we minimize submodular functions? Naturally, we may be interested in minimizing submodular functions that don't enjoy monotonicity, since then it might be a little bit easier to minimize them. For example, subject to a constraint like cardinality less than k. Okay, so let's turn to let's turn to this problem. So let's look at the situation where we have a Matroid constraint. So instead of a uniform Matroid, let's let I be the independent system of a general Matroid. And ask, what can we now say about our maximization problem? Maximize f of I subject to I in belonging to the Matroid. So let me give you an example of this problem, and this example by itself is going to show that we can no longer get our 1 minus 1 over e. So this is an important example that actually is going to motivate what's going to come in the sequel when we start talking about continuous extensions. And the problem is called the submodular welfare problem. And it goes as follows. We have n items to distribute to m agents. And each item has to be given to exactly one agent. You can't split the items. You can't assign one item to two agents. So each item must go to one agent, but one agent could collect more than, could be assigned more than one item. So each agent receives between 0 and n items. So conceivably we could allocate all of the items to just one agent. And the key assumption, which is the word submodular in the name of the problem, is that the utility of each agent is a submodular function. So we assume that the utility of agent I is a submodular function. So in other words, the utility of agent I is some submodular function fi of S, the subset of possibly empty, possibly everything, the subset of possible items that are allocated to agent I. And it's also monotone. So that means that agents only become happier as they get additional objects, items. And the goal is to allocate the n items in order to maximize aggregate utility, which means the sum over all the agents of their utilities. And I'll write this as fi of si, and of course we need to have the si's, their union being everything, and they have to be disjoint. So here's an exercise, is for you to show that this problem is an example of monotone submodular maximization subject to a Matroid constraint. And the Matroid constraint is, in this case, it's not going to be the uniform Matroid constraint. So the exercise is show that the submodular welfare problem is of the form that I've written here. It's of the form max f of I subject to I in I for I a Matroid. I a Matroid and f some monotone submodular function. Okay, so this is a generalization of what we saw before. And now let's look at a specific example so we can examine how well greedy does. And we're going to see that actually greedy is not going to do better than giving us a 1/2 approximation for this problem. So that, in some way, is bad news. It's telling us that now this problem is certainly harder, or at least it's not as friendly to greedy as when we had the uniform Matroid. So here's an instance, a very simple instance, an instance of the above problem, and we're going to see very simply that greedy gives a 1/2 approximation. So we have n is equal to m is equal to 2. In other words, we have 2 items, and we have 2 agents, and the welfare function of agent 1 is very simple. Agent 1 only cares about the first object. So in other words, for any subset S of 1 and 2, this is object 1, this is object 2, then the welfare of agent 1 is equal to 0 if 1 is not in there, and it's equal to 1 if 1 is an element of S. So whether or not agent 1 gets objects 1 or objects 1 or 2, he values that bundle equal to 1. And if he doesn't get object 1, he derives no value from it. Agent 2's welfare is 1 if she gets only object 2. It's equal to 1 plus epsilon if she gets only object 1. And she also gets 1 plus epsilon if she gets 1 and 2. So in other words, our second agent values object 1 slightly more than she values object 2. And if she has object 1 already, then she doesn't value object 2 at all at this point. So you can see how we built this example. So what does greedy do? Greedy is going to decide what to allocate. So greedy will gives element 1, or I guess I've called it object. That doesn't matter. Gives element 1 to agent 2 because she values it more than agent 1 values it. But at this point, we have one more element to allocate, and now that we've already given element 1 to agent 2, neither of the two agents value element 2 at all, and therefore the greedy value is the aggregate welfare, which again is just how much value agent 1 gets plus how much value agent 2 gets, and we can write it like this, since we can only allocate each element to only one of the two agents. So greedy has 1 plus epsilon aggregate welfare. Agent 1 has welfare 0, and agent 2 has welfare 1 plus epsilon. But obviously the optimal is to give object 1 to agent 1 and object 2 to agent 2, and that gets us 2. And since epsilon was arbitrary, we can therefore see that greedy is not a 1 minus 1 over epsilon approximation, but something a little bit worse, a 1/2 approximation. So that's the bad news, and we could similarly ask, how bad could greedy get? So the good news is that actually greedy is always going to give an at least 1/2 approximation. So actually this is a guarantee. This is the previous small example was an illustration of how poorly greedy does, but turning it around, it's also an illustration of how well greedy does. There's no example which causes greedy to do worse. Again, assuming we have a submodular function that is also monotonic, and our constraint is any Matroid constraint. So let's write that as a theorem and see the proof of that. For f, a monotone submodular function, and for I, any Matroid, the greedy algorithm guarantees a 1/2 approximation to the problem that we've been talking about. Matroid, monotone submodular optimization, maximization, subject to an arbitrary Matroid constraint. Now let's see how this follows. So we're going to use some of the same ideas we used in the proof of the greedy algorithm for the uniform Matroid. And in terms of notation, we're going to try to follow the same ideas there that we gave in that lecture. So let's let s hat be the greedy solution, and let me order the elements of s hat as I'll use G for greedy, G1, G2, G3, etc., all the way up to GK, and let me order that so that any subset is going to be the output of the greedy algorithm at that iteration. So in other words, I've ordered the elements in the order that the greedy algorithm added them in. So in other words, Si is going to be equal to G1 all the way up to Gi, and therefore Sk is the output of our greedy algorithm. And again, to match the notation of the previous lecture, let's let C let C be the optimal solution. And I'll use O1, O2, etc. up to OK. Denote the optimal solution. So now note that I wrote G1 to GK and O1 to OK. I used the same index, but we get this basically by the Matroid constraint and by monotonicity. So by monotonicity, this guarantees that the optimal solution and the output of greedy is going to be a base. S hat and C are bases of the Matroid, and we already have seen in our many lectures on Matroids that all bases have the same number of elements. So we're justified by using K for this. Now, in one of our later lectures on Matroids, and in particular leading up to talking about Matroid intersection, we proved something stronger than the exchange property. So recall that we proved, let me call this a strong exchange property for bases, which says the following, that in the directed graph D of S hat, we showed this for any independent set, there is a perfect matching on the symmetric difference between any two bases, and I'm going to apply to the two bases S hat and C. So let me draw this picture because it's to remind you of what we had said. So this is my basis S hat, and then I have some other basis. Possibly it has some overlap. We know that it has the same number of elements. So let's suppose it has overlap 1. So this is my other basis C. Then the symmetric difference is going to be these 6 elements. And the theorem tells us, remember the graph D of S hat, the directed graph, has an edge from the independent set on the left to the complement. So this set here is E minus S hat, has an edge if I can swap those two elements and still remain independent. And what we saw is that there is a perfect matching, and in particular, and moreover I should say, we can swap all of those elements simultaneously and still stay an independent set. So this is the theorem. So there's a perfect matching that allows me to do this. And so what does that mean? This perfect matching tells me that if I reorder the elements, if necessary, if I reorder the elements O1 to OK, I can do it in such a way that swapping one at a time will maintain independence. So in other words, thus we can reorder the elements from O1 up to OK if necessary, so that if I start with my optimal greedy solution and I subtract any element gi, then I can add the corresponding element oi and still be an independent set. Okay, so this is what we've got. Now let's see how we're gonna use this. So by the definition of how the greedy algorithm operates, what is the marginal value with respect to sets with respect to the elements that greedy has already added by iteration I of that next element that greedy added. Well, by definition of greedy, what does greedy do? It looks at the set it currently has, and it adds the element that has the largest marginal value. So certainly this is at least the marginal value, again, with respect to the elements that greedy has already taken up to set I, of that matching element in the optimal set. Okay, so now let's use this to come up with a bound on the value that the greedy algorithm gets. So just by a telescoping sum, this is equal to the sum from I equals 0 to k minus 1 of f of, these aren't marginal values, f of si plus 1 minus f of si. Okay, there's nothing here, it's just by telescoping sum. But then again, this is now the definition of the marginal value. So by definition, this is the marginal value of element gi plus 1 with respect to the set si. And by virtue of this inequality, this is, in other words, by virtue of how greedy operates, this is greater than or equal to the sum of the marginal value of oi plus 1. And now I claim that this is greater than or equal to the marginal value of oi plus 1 with respect to a bigger set. Again, this is a basic submodular property of s hat of oi plus 1. So this is just using submodularity and the fact that the marginal values decrease as we have larger sets or containing sets. And now this is greater than or equal to f of s hat of all of the o's. So this takes a few steps to see, and I'll leave that I'll leave that for you to check as an exercise for you. And just note that one simple way to show this is that if f is submodular, then for any set, and in particular the set s hat, the marginal value f s hat is submodular. So recall that I can define the marginal element of an element, or even as an entire set. So the marginal value of an entire set, I'll just write out what this is. This is f of c union s hat minus f of s hat. So seeing f subscript s hat itself as a set value as a set function, you can easily check that is submodular. And by submodularity of that, basically just using the basic definition of submodularity, you can see that we have this. Okay, so now this is greater than or equal to f of c minus f of s hat, and this is just by monotonicity, because this term here, f of c union s hat, that is certainly no smaller than just f of c, because I'm evaluating on a smaller set. So this is by monotonicity. But this essentially concludes the theorem, because now I have f of s hat on the left, f of s hat on the right. Moving things over, I get my desired conclusion that f of s hat is at least 1/2 f of c. And we saw from that simple example with two agents and two elements that this is tight for greedy, so we can't do any better. So in the previous lecture we saw that greedy on a special matroid, the uniform matroid, gives us 1 minus 1 over e, and for a general matroid constraint, again assuming we have monotonicity, we have a 1/2 approximation. We're next going to turn to more general optimization problems and see what we can do there. And what we're going to need is something called a a continuous extension. So that's what we're going to do in the next lectures.